recently measured. Let me just I'm going to tell you about this first determination of the B Kν decays that have been made by Belle-II. And this is an exciting topic in flavor physics. First, because it's the first decay of this kind that's actually measured experimentally. And also because there is some small deviations that from the expectations that we had. So we're all looking forward to see how this is going to evolve with more data, even though it's still preliminary to get to any conclusion. And this presentation will be based on these two papers. So the first one was in collaboration with Damir Becirevic, who is my colleague here in Olcyr, and Gioacchino Piazza, who was a PhD student here, who is now a postdoc in Zurich. And the second one that was done in collaboration with Lucas Alvischer and Salvador Rosario, in addition to the other two guys. And my goal today is to explain what these decays are, why they are interesting, what is the status of the standard model predictions, and what we actually hope to learn from them. All right, so let's start. And I'd like to start with a brief introduction about the flavor physics program and what we would like to achieve. And of course, our motivation here is the old fact that the standard model is it's extremely beautiful theory, but it has to be an effective theory at low energies of a more fundamental theory that we still don't know. And there are many motivations for that. I'm not going to list them: hierarchy, flavor problem, dark matter, and so on. But of course, this motivates the quest for physics beyond the standard model that should be done in all possible ways. And flavor physics is one of the possibilities that we have. So when we say flavor, we refer to the fact that fermions, they appear in nature as almost identical replicas that are only distinguished by their interactions with the Higgs boson in the Yukawa sector. And flavor physics is precisely the study of phenomena with flavor changing, transitions, and CP violation. So when you do flavor physics, we have two main goals, if you wish, which are on one side to try to identify new symmetries that would be horizontal here and relate to different generations in the same way that decay symmetry appears vertically here. So we don't have that in the standard model. And the second one is basically the search of new physics phenomena through precisions, and these B Kν decays are one example. So the first question is very fundamental, and it's one of the big problems of the standard model. And to understand it, I think it's very instructive to compare what we know about the gauge sector with the flavor sector. And the reason why the standard model is so successful, flow, high energies, and that allowed us to compute even quantum corrections, is the fact that it's a theory that's pretty much fixed by a symmetry principle, so the gauge symmetry, that leaves very few parameters that you have to fix by data. So if you compare that with the flavor sector, the situation is quite the opposite. So the flavor sector is pretty much unconstrained in the standard model. It's very loose. And that's because we don't have such a symmetry in the standard model. So flavor appears in the masses and mixing of fermions, and this can be described by the Yukawa interactions that are shown here. But for that, you have to fix many parameters by comparing data and experiment. So that's already uncomfortable, because you have many parameters that you have to fix. So you'd like to be minimal. But more than that, this is a problem because when you look at the values that these parameters take, we see some clear patterns that do not look an accident. Examples are the fermion masses here in the logarithmic scale that have a huge hierarchy between the neutrinos and the top quark and the electron. Okay, so where the only missing piece here is the absolute scale of neutrino masses that we still don't know, but still you can see that there's a huge split. And also we do not understand why there are three families and why the mixing of quarks and leptons by the CKM and the PMNS matrices are so different. So to explain all these questions, so the symbol of all these questions is what we call the flavor problem. And if you want, this is the goal, the dream of flavor physics, to have a simple ultraviolet theory that would explain this in a more fundamental way. As you can imagine, that's a very difficult question to answer. And having a guidance from experiment would be extremely useful. And this connects with the second point that I mentioned before. So when you make measurements at low energy of decays of specific observables, this can also be a very useful way of looking for new physics indirectly. And the idea is pretty much simple. So if you have a quantity that you can predict very well, and that you can measure very accurately, you can look for deviations that would come from particles that would virtually contribute to design. So here you have an example with a specific B meson decay that would receive contributions from a charted scalar, so a particle that we do not have in the standard model. So this is the idea, and it's very powerful because we can probe energy scales that go well beyond what we can do with current colliders. But of course, there's a caveat here that you have to keep in mind, is that not all observables that are measured at low energy can be used to this purpose. So they have to meet certain conditions, criteria, in order to be good observables in this regard. And first, so they have to be sensitive to new physics, and that means that they should be rare in the standard model. We should be able to handle QCD, which is a big problem here, in that since QCD is non-perturbative at low energy scales, and so we do not have a complete analytical ab initio understanding of that. So we have to choose observables that are only mildly or have little sensitivity to these hadronic uncertainties. And lastly, should be something that we can actually measure experimentally. And the rare meson decays that I'll be discussing, there are a good example where these criteria are all satisfied to a good extent. So this is for the search of deviations. Of course, there are also processes that are strictly forbidden in the standard model by this accidental symmetry that remains when you break the symmetry of the gauge sector with the Yukawas, that imply the conservation of baryon number, lepton number, and lepton flavor. And these are extremely clean proofs of new physics, because here this question about the hadronic uncertainty is of course secondary. So the standard model prediction is 0, so any signal would be a confirmation of new physics. I'll not be discussing those, so I mentioned them just to be complete, but this is of course something to keep in mind, because they are very important elements of the precision frontier. All right, and then the question is how we do this. So when you do flavor physics, you have many different scales, from the big quark mass, the top quark, that's very important for all these processes, and also the scale of new physics that should be above the TeV. So when you have separate scales, we have one approach, the effective Euler approach, that's very useful to make systematic and precise predictions. And that allows in particular to have a general parameterization of new physics effects from whatever source of new physics you could imagine. And the idea is really simple. So if you take a specific process at low energies, and if it's mediated by some heavy dynamics beyond the standard model, at low energies, if you don't have enough energy to resolve the propagation of these particles, you only see contact interactions. So a series of contact terms that can be parameterized by this infinite series of non-normalizable operators that have the coefficients here that encode the short distance part, and that are called the Wilson coefficients, and that are suppressed by inverse powers of the EFT cutoff, so the lambda scale. That means the scale of where these particles actually live. And that it's an infinite series, but that can always be truncated given the experimental precision that you want to achieve, since the higher order operators are more and more suppressed. And when you do so, you have very few parameters. No, yeah, not necessarily. You have a finite number of parameters that you can try to fix by using data. Okay, and this is pretty much general, and that's why we like it. And the idea, of course, is that the dream is that one day we would see some kind of deviation, or we would see a phenomenon that can explain by this more general EFT, but not in the standard model. And then this could be a hint that would allow us to then figure out which kind of beyond the standard model scenario is actually realized in nature. Well, pretty much as how the Fermi theory was formulated before the gauge sector of the standard model, and there are other examples you can think of. So far, we don't have a clear indication of such a situation, but so most of the searches are negative, but still, it's important to keep in mind that this is also a useful piece of information. And here I show, for example, the operators that matter the most for flavor physics are the ones of dimension 6. dimension 5, you only have one operator, one type of operator that's actually related to neutrino mass. Let's forget that today. And for these dimension 6 operators, if you set these coefficients to be 1, and if you try to see what is the suppression that you need in order to comply with flavor data in different sectors, you see that you get values that are very large for the scale. For example, 10 to the 5, 10 to the 6 TeV in the Kν sector, and also in this lepton flavor violating process. And this, even though we don't have a signal of physics, it's a very important piece of information, because it tells you if you want to do physics at the latency at the TeV scale, or if you want to try to solve the hierarchy problem that points precisely at the TeV scale, you have to be extremely careful on the way you couple to fermions. So you have to protect somehow and suppress rare and forbidden processes, such as the ones that appear. And that's a very useful input for model building. And there are actually ways that people have realized for doing that. So, such as minimal flavor violation or specific flavor symmetries that would suppress flavor violation. Okay, so this is all I wanted to say for the introduction. I'm good with the time. And now we can move to the main topic of this presentation, which are the B2K decays.
I'm sorry.
Please,
can I
go.
Ask you about this plot, please? For instance, each observable here is fed by, let's say, different 6-dimension operator in your from your Lagrangian, or
yes,
it's not one-to-one, right? It's each observable.
There are many, yeah.
Yeah.
In some cases, it will be hundreds of operators. So here, I think that for the example, they selected one specific operator for each process, and they set the limit on this lambda scale. Yeah.
Okay.
But for one operator, of course, there are many of those. And then when you do this analysis, if you want to be systematic, you have to take into account for these many operators that could appear. But thanks for the question. I went too fast here.
Mm-hmm. Thank you.
And yes, and just to comment, so these hatched areas here are precisely what happens when you, for this scale, when we impose what we call minimal flavor violation, which is one of the ansatz that you can have for these Wilson coefficients. And you see that you can have a much smaller value of C, so then also a smaller value of lambda around the 1 to 10 TeV scale, which is what we're looking for at the latency. Okay. Other questions? Okay, if not, so let's then go to the core of this presentation, and this will be in 3 main acts. First, we'll talk about the standard model description of these processes, then I'll present the Belle-II results, and then I'll discuss what we can learn from them, both within the standard model and also beyond. And here is just a quick recap about flavor changing neutral currents. So this is the case that I'm talking about, is a B quark that goes into the S quark. So it's precisely this, right? Flavor changing neutral current. And it's in the standard model, we have this very special feature, which is that these processes, they're completely absent at relay. So the couplings of the Z, they will be flavor diagonal. And the only place where you can actually have flavor violation in the standard model is in the couplings of the W with the up and down quarks, where they have the CKM matrix that appears here through this misalignment between the components of the left-handed doublet. So the CKM matrix is this matrix with this very special feature. So we have large numbers here in the diagonal, and then it becomes smaller and smaller when you go further away from the diagonal. So that means that flavor violation is already suppressed by the CKM. And when you want to have a B quark that goes into a S quark, you necessarily need to pass through the charge-discovery interactions for the reason that I just told you. So you need to put a top quark and then the W loop, and then that's how you can get this kind of processes. So with 2 insertions of the CKM, you have processes that violate flavor by 1 unit. And if you insert them 4 times, then you can have, for example, the oscillation of a frequency of a B sub S and B sub S bar mesons. Okay, but the important thing here is that since these are loop and CKM suppressed processes, they're very rare, so they can be good probes of new physics. And also, in most of the cases, they are dominated by short distance physics. And by that, I mean that when you look at the amplitude of the B2S lepton-lepton process, thanks to the gene mechanism, we know that the leading contributions to this will be proportional to some product of a CKM matrix element, and then the masses of the particles, the fermions that are running in this loop. So the top quark will give the leading contribution here. And that's very important because then it's easier to separate what's short distance and long distance within this EFT approach that I mentioned before. All right, so you have heard before about the B2K muon or B2K star muon decays. So K is a pseudoscalar, and K star is a vector meso. And you know that they have been extensively studied at LHCb, for example, and also a bit at the B factors. And here I make a comparison with the modes with neutrinos to explain why they're interesting. So starting with the case with muons, they're of course rare, so they're sensitive to their physics. We have good experimental setups that allow us to look for them. And the nice thing about muons is that you can have many observables because this, with a K is a 3-body decay, with a K star, the K star decay, so it's a 4-body decay. So there are many angular observables that you can define in addition to the branching fraction. So there are many things you can measure, predict, and look for deviations. But the big problem with muons is that they are theoretically challenging on the standard model side. So if you want to compute this process, you have to account for this kind of contributions with the charm quark here that are very important. First, because so the charm quark is a light of degree of freedom. Okay, so this is a contribution that where you cannot really factorize what is short and long distance. And also, you know that there is a region here where the CC bar, they can go on shell and produce a plethora of CC bar resonances. So first of all, in this resonant region, there is not much you can do. You will not look for new physics there. So we usually cut that away. But even outside, it's always unclear if we really understand these contributions, these non-resonant CC bar loops that are very difficult to predict for the reasons that I just mentioned. And the big advantage of the case of neutrinos is that we don't have this problem because the photon will not couple to neutrinos. So when you compare this differential branching fraction here, it's a much smoother curve that's much easier to predict. And in addition to that, they have the same advantage that we have with muons, in the sense that they're also rare, so sensitive to new physics. They are a bit more experimentally challenging, but in B factors it's possible to measure them. And they're theoretically cleaner. So that's the main motivation. And I should also say that here we have information mostly with muons, but with neutrinos can be of any flavor. This is some kind of inclusive measure. So you're probing the electron, muon, and tau flavor, and that's very interesting, especially for the tau that's very hard to measure otherwise. Okay, so that's why we want to study that. Now, for the standard model description, when you integrate out W and the top quark, the leading contribution that we have is parameterized by this effective Lagrangian, where you have V minus A times V minus A operator with this CL, which is the Wilson coefficient that can be computed in perturbation theory. So, and this comes from this box, penguin diagrams. And right now, thanks to this incredible effort of these people, we know them, including even QCD corrections and electroweak corrections. This is something that started in the 90s, and we also had some quite important contributions in about 10 years ago when these electroweak contributions were computed. So we know them very well with a percent perceived, and this so this is the part that we understand quite well. But then we still need the CK matrix element that will be a parametric input here. So this VTB times VTS. That will call lambda t. And we also need some input about the QCD, so what is going on in this decay. So for the hadronic matrix element that we need, the idea is basically that you parameterize this in this the most general way in terms of a product of Lorentz factors and then functions that we don't know that we call form factors. And for this, use Lorentz symmetries and everything that you have at your disposal. And then we try to have some non-perturbative calculation of that, for instance, with numerical simulations of QCD on the lattice. That's by far the best option that we have so far. And I'm going to describe that in a bit, but let me just say that CKM is also important, as I said, because you have to specify in which way you are fixing this element. And the usual strategy is to try to use the unitarity of the CKM. So you relate, for example, VTB times VTS to VCB plus higher order corrections on the Wolfenstein parameter. And then in principle, if you measure VCB, you can get the lambda t that you need here. But that's not so simple because there's not a unique way of getting VCB, and they do not quite agree. So these are the two main challenges that we still have in order to predict these quantities. Now, for the form factors, let me just give you the example of the decay that was measured experimentally, and for which we have a better control on the lattice, which is the B2K transition. So pseudoscalar to pseudoscalar. So here you have this matrix element, and then you have two Lorentz vectors. And then if you write this in the most general way that's allowed by your symmetries, you know that you can have a combination of Lorentz vectors like P plus K and P minus K. So that's what I call here Q. And then there is just some rearrangement here, but just to say that there are two independent functions that you can write down, this vector and scalar form factors. And we know from first principles that they must agree at Q squared equals to 0. So Q squared is the lepton invariant mass. And we know more or less their shape. It should be something that should have a polar form. Here I'm factoring out these poles, and that this comes from the analytical behavior of these amplitudes. And then what you do is that you compute these form factors at specific values of Q squared, at high Q squared, where you have lattice data. So these are the points that we have here. And then you extrapolate to the whole region using this constraint here on the value at 0. That's how you get these form factors. And then dashed line was the situation, I think, in 2021. And this is a fit that we did with recent lattice data that gets much better. And then even at the few percent precision over a big part of the phase space. Okay, so these are the numbers then. So the form factors are understood quite well, at least for this decay. And here you see the different lattice calculations, and they all seem to agree. And I also superimpose here this specific calculation that does not use lattice QCD, but combines that with some model approach, like Consum rules, and you see that the value is a bit off. But anyway, so the important thing here is that we're reaching a few percent precision, so that's very good. But at the same time, it's a bit scary because it's very difficult to do hadronic physics at this level of precision. Then there's always a question if these results are really robust. And this is an important question because, as you can see, that they're dominated by one population that is more precise than the others, and also because we have to rely on this extrapolation. So to cover the entire physical region, you are actually not using the direct lattice calculation, but the result of some extrapolation that will depend on the parameterization that you choose. So it's very important to have ways of cross-checking if these are reasonable inputs. And if this extrapolation is done correctly. And here is just one of the proposals that we made, which is that if you take this case with neutrinos in the low Q square region and in the high Q square, so you split your beam, you take two beams at low and high Q square, and you make this ratio, it's a very interesting way of testing this extrapolation because, so the unknown CK matrix element will cancel in this ratio. We also cancel the form factor normalization, and also potential uniphase contributions with some reasonable assumptions. So in the end, this is really a test of the shape of these form factors and if this input that you are using to fit the lattice data is reasonable or not. And here, for example, the predictions that could be used to compare with experimental data. So this is the new result, and this is the old one. You can see that they're a bit different. We still don't have this differential information, but it will be very interesting to have that. Okay, so this was the first piece, and the second piece, which is actually the dominant source of uncertainty as of now, is the CK matrix. So as I mentioned before, if you take VTB, VTS, that's related to VCB. And then VCB, you look for charged current decays that have turn a B quark into a C quark. And then experimentally, people can look for a vector meson, a pseudoscalar meson, or what we call an inclusive measurement, where you have all particles that have a charm quark. And as you can see, depending on what you take, you get a different value of VCB that then implies different value of VTB times VTS. And this is a bit of a problem that we still have to solve. So just to comment, you can compare this with this global fits that take into account all flavor observables and that seem to prefer the inclusive value, but it's still very early to say anything. And I should also mention that recently some people proposed that instead of using the 3-level decays, we could use actually a loop level observable that's also proportional to VTB, VTS, namely this oscillation frequency of the mass difference of BS and BS bar mesons that's predicted in the standard model by these loop diagrams. Okay, that's a good idea, but it doesn't solve the problem because here you also need some hadronic input that we call the back parameters of this B hat. And here are the latest determinations for this, depending if you have the number of dynamical flavors that you have in your simulation. And you see that there is a disagreement that's not completely clarified, especially because the simulations with 4 dynamical flavors, they will rely on a single lattice QCD result. And depending on what you take, you have a value that's close to the inclusive one or the exclusive one, so it doesn't really solve the problem. But it's clear that it will be very important to solve this if you want to predict these observables precisely. I'm going to show you the numbers soon. It's not a problem as of now, but it will be a problem when you think about Belle-II with all the data that they are planning to collect. Okay, so this is, I wanted to say something about how difficult it is to get VCB. Yeah, so I think I'll skip this slide. I can come back if you are interested. Okay, and now finally, the measure of Belle-II is with the case with a charged meson. Okay, so a B plus that goes to a K plus. And I've been saying that these are loop level processes, and yeah, that's true, except that there is still one 3-level contribution that can appear, and that to the order GF to the 4th, and that only appears for the charged meson where you can have a B plus that decays to a tau neutrino, that this tau goes on shell and then decays to a K or K star neutrino. And if you estimate this is about 10% of the loop level branching fraction that I mentioned before. So in spite of the GF to the 4th suppression, since the tau is on shell, that's not entirely negligible, that has to be taken into account. And for this Belle-II analysis that I'll show you today, so what they decided is to completely remove this contribution by including it in the background and exploiting for this the flight distance of the tau that in principle they can resolve. Okay. And here was the situation until 2022. So we had upper limits for the different decays of pseudoscalar and vector mesons. These are the red lines here. And if you compare with our predictions, they are shown here. The certainty is quite small for the K. It's bigger for the K star. And the decays that Belle-II measured is the first one, B plus to K plus new. So to take home from this first part of my presentation is that we have a reasonable understanding of these uncertainties given the experimental errors that we have now. But when you extrapolate this for the future Belle-II sensitivity, we must have a much better understanding of the form factor uncertainties that are shown here, and in particular the CKM matrix that introduces a sort of ambiguity. And for that you need a lattice QCD information, but also it will be useful to have some kind of experimental information on the Q-square distribution that will be very useful to constrain what we're doing, for example, with these form factors. Okay. All right. So now let's move on to this result. And then you may be wondering, so how do you measure a decay that has a B, a K, and then missing energy? So that seems very hard. And this is possible at the B factories, thanks for 2 reasons. So a B factory is a E plus E minus machine where you actually tune your energy to sit in a specific resonance, namely the upsilon for S, that will produce lots of BB bar mesons. And then, so in this setup, you know the center of mass energy, okay? You produce a lot of B mesons. And the very special feature here is that it's pure quantum mechanics. So you produce a coherent pair of B and B bars. So what you do is that you look on one side of your detector, and if you see a B meson, you know that you have a B bar on the other side. And so that's how they can reduce the background in spite of the large amount of missing energy that they have. So this is the strategy. And then the only, so the important difference between the different analyses here is how you decide to tag, so to observe the one B meson on one side. And there are several strategies that have been used so far, and they can use a specific decay. So for example, hadronic decay of this B meson, it can be a semi-leptonic decay where we still have some part of missing energy. And what was new of this Belle-II measurement is that for the first time, they do a combination of many channels on the tag side. And this is what we call the inclusive tagging. And depending on what you do, you have a bigger or smaller efficiency, but the price to pay is that if you have a big efficiency, you also have a large background. So, and that's to keep in mind. And so Belle-II, as we're going to see, they did a hadronic and an inclusive analysis, while the Babar and Bell, so the previous experiments, they did the hadronic and semi-leptonic one, but not the inclusive. And here are the results. So the previous results are shown by these blue points. Okay, so we didn't have a clear observation of signal away from zero at 2, 3 sigma. So this was the first analysis by Belle-II using this inclusive method. And what is impressive is that they have a comparable precision with older results that had about 10 times more data. So, and this is the power of this inclusive analysis. And in the one that was released, as I said, they have an inclusive result, they have a hadronic one, and they have the combination of the two. So as you can see, the standard model prediction is shown here by the yellow line, and the one that deviates clearly is the inclusive one. Okay, so that's something, of course, that's very important to cross-check when you have more data. And while the hadronic one, so it agrees with the inclusive one, but it also agrees with the standard model and also agrees with 0 at 1 sigma. So they don't have enough data still to distinguish from the background. But it will be very important to see what the different tagging methods are giving when they have more data. Okay, so any questions about that? And if you look at the central value of the Belle-II measurement, this is the number, and it's quite large compared to the standard model value. Okay, so it's a factor of few larger. So it's a very large value. All right. Okay, so now what can we learn from this B2 Kν decays? And this is something you probably heard about. There's still a number of anomalies, and people call them in B2K and B2K star mu decay. So this comes from global fits where you have the differential branching fraction of these decays, and also several angular observables that are then fitted, for example, with this effective Lagrange. You have an operator that's called C9 that has a vector coupling to the leptons, and one that's called C10 that has an axial coupling. And these are the results by several groups that have tried to fit this data. And it seems that there is a preference for a negative value of C9 mu, so the coupling to the mu's. Okay, so this is of course interesting, but here the big problem is I mentioned these diagrams with the charm loops that are very difficult to compute, reliable. We don't know how to do them ab initio. And if you think about this diagram, we have a vector coupling to the mu. So this is precisely what could mimic a value of C9 mu that is non-zero. So that's the main reason why we are cautious. And here it's very difficult to say if this is actually new physics or if it is some hadronic uncertainties that's underestimated, for instance, from this diagram. So just a side comment, LHCb had the measurements of this lepton flavor universality ratios, and they were interesting because this kind of contribution would cancel there. So that's why we're so interested by this kind of measurement, but then you all know the story. In the end, there was a problem with the experimental analysis, so there is no deviations on this. Okay, so the problem remains. And I think the case with neutrinos, they can be interesting because for the following reason. So here I plotted the differential branch fraction with muons and neutrinos for the B2K. So look at the left panel. And as you can see, they are very similar when you stay away from this Charmonian resonance. And that's because So when you think about this, the mu mass is also negligible in comparison to the energy scale of this problem. So you have the same CKM matrix element, and you have the same form factor that will dominate this branching fraction, so this vector form factor. So this is also true to a smaller extent for the K star, but in particular for the B2K decays. So when you make this ratio between the two, the CKM matrix goes away, and also the firm factors to a good extent following this plot. So then the only unknown that remains, if you assume that there is no new physics, would be this diagram that would like to understand better. So by doing this ratio in different beings, it will be a way of extracting this diagram and checking, for instance, if it has a specific Q-square dependence and so on. So that's why that's, I think, a good way of using this data in the future when it becomes more precise to learn more about this in their model. And here's just an example. I don't expect you to read all of this. Just look at this plot on the right side. Is, for example, the dependence on this ratio when you vary an effective value of the C9 mu in a specific beam. And the blue line is the one from the K decays, and you see that there's a small slope here. So if we're able to measure this quantity, you can extract this value and then try to compare it with people who are trying to understand this on the theoretical side. All right, so this assuming that there is only physics, of course. All right, so, but now let's go back to this Belle-II data and let's see if this deviation that is about 3 sigma can be actually be explained consistently in scenarios beyond the standard model. And here I use again an effective Lagrangian. So the first operator is just the standard model one, where now I have a coupling with that can have different neutrino flavors and they can be different for them. So that's why I have the I and J indices here. And then you can also have an operator beyond the standard model that has a different chirality for the hadronic current. And if you assume that neutrinos are left-handed, that's all you can have. So there are only 2 couplings, and then you can compute these branching fractions with a K and a K star. So here is an expression, don't read it, just notice that there are terms that are the same for the K and the K star. And then there is a last term, so the interference between the left and right operators that only appears in the case of the K star. So already here you can see that there is a complementarity that's increasing, especially when Belle-II will also measure the second type of decay. And here is our interpretation of this measurement. So the vertical band is the experimental result that's 3 sigma away from the red point, which is the standard model prediction. As I mentioned before, standard model uncertainties are very, very small compared to the experimental uncertainties now, okay, but this will change in the future. Here, this shaded region is the exclusion for the B2K star new decays that comes from the old B factors, so in particular Belle. And then when you take this standard model here, and if you turn on a left-handed coupling, you get this orange curve. And if you turn on the right-handed coupling, you get this purple magenta curve. And as you can see, they are quite different. And the ones that's preferred from data, it seems to be the right-handed operator, even though you cannot exclude the left-handed one yet. And finally, let me just mention that if you turn on both couplings at the same time, so left and right-handed, you can cover this entire region except for the shaded area below here that's not accessible within the EFT approach. So let's say that's forbidden theoretically. All right, so you have to be here. Okay, very good. So so this is the situation. The measurement of modes with K star will be very interesting. And they are also interesting because the K star always decays. So K star goes to K pi. And even though you have no information on the missing energy, you can actually measure the angle between the K-on and the pi. And that gives access to an angular observable that we call the FL, so the longitudinal polarization of the K star. And here's the standard model prediction. And here we showed the ratio of FL by the standard model value and how it changes when you turn on these new physics couplings. For the left-handed one, you have absolutely no impact, so it remains standard model-like. But for the right-handed one, and in particular for this region that explains the Belle-II data, you see that there is a huge depletion of this quantity. So this kind of measurement that was first proposed in this paper by Buras, of Mashofer, and so on, it will be a very good test of if this signal that they see is in physics or not. Okay, so that's all I wanted to say in this low energy effective field theory, but you can always go one step beyond and try to formulate these operators with an FT that satisfies the full standard model gauge symmetry. And basically you have to do that because we know that in physics must be well above the electric scale. So in the end, when you want to match to realistic models, this is the FT that you need. And that's an interesting thing to do also because then you have to put neutrinos in a doublet. And when you do so, you get correlations from the same operator between the modes with neutrinos and with leptons. So I didn't say anything about flavor because I didn't have to for most of the plots that I showed before. But here it becomes very important, and then you can actually probe the flavor of this operator by combining the information with neutrinos, or that are inclusive, with the charged leptons where you know the flavor. All right, so if you want to do so, there are basically two operators that would contribute at reliable. So in this math, you could have something like this. So this Higgs current operator that induces a non-diagonal BS-Z coupling that then would couple to neutrinos universally, or you could have a four-Fermi operator. And here, the first type of contribution is actually has to be very small, because if you change neutrinos by muons here, you can induce B sub S mu that's very well constrained by the LHC experiments. And also, if you insert twice this BS coupling, you get B sub S, B sub R frequency that's very well measured and predicted. So this will be a contribution that's way too large. So we know that this cannot explain data. So the only thing that can actually work are these four-Fermi operators. And they can be of different kinds. So what I shown here is that the four-Fermi operators that you can write down that would induce a contribution to BS neutrino. So capital L is the lepton doublet, capital Q is the quark doublet, and then this is the weak singlet down quark, and here the same for the leptons. So the operators with the blue band here, they contribute to the decays with neutrinos, and the ones in orange, the one with charged leptons. And if you try to fit current data by using the operators that here have the neutrinos, you see that you get this kind of solution. So this green blob, where the information from the K and K star are complementary. So you end up with this region here that correspond to any physics that can be up to like 5 TeV if you assume that this coefficient is 1. Okay, so large, but not too large when you compare to what we're probing at LHC. And then you can open up these operators, and as I said, the doublets have the charged leptons and the neutrinos that appear in different ways. And you can ask which is the flavor actually of these operators that can explain current data. And this is the study that we did with these guys. And the conclusion was basically that if you try to couple to the muons and the leptons, because of B sub S mu and other quantities, you cannot explain such a large deviation. Same for if you assume that you have a non-diagonal coupling, so let's say mu tau, then you'd have also some low energy decays that are very well constrained. So the only viable option are the couplings with the taus, and that's because we have very few constraints at low energies for this B2S tau decays. And you can actually make a prediction, and you expect for this viable region where you explain current data, an enhancement of factor of 10 with respect to this scenario. Okay, that's interesting, even though it's still very experimentally challenging because the tau is an unstable particle. So if you try to measure this, it's very difficult to get to the region that's favored. Okay, but you can go one step beyond and then plug in specific models that would generate these viable operators. And that's interesting because then you can make more predictions, and there'll be other ways of testing these scenarios. And there are basically two ways that are the simplest ones. So you could have a Z prime that would couple to BS and then to the tau, or you could have what we call leptoquark. So a colored scalar or vector particle that would couple here in the D channel. And here I give an example of one that would give precisely the right-handed operator. And for the Z prime, it's really hard if you assume it to be heavy, because we know that the couplings to the quarks have to be very small, because if you insert the BS twice here, BS bar, S bar B, then you get again the mass difference of the BS system that's very constraining. So if the couplings to the quark is small, and if you want to fit the data, the couplings to the taus have to be very large. So it's very difficult to have something with a perturbative explanation, assuming Z prime to be heavy. And there, I'm certain that there will be also LHC data that would cut these models out. So what can work is the leptoquark, and that's because when you look at the B sub S, B sub S bar, and here there's a typo, here should be an S, and here a B, sorry. And this is a process that will appear at loop level in these models, and that it's much more easier to comply with these constraints. And actually, if you combine the experimental information on the meso mass difference and with B Kν, you can set an upper bound that has to be satisfied for these masses, which can go beyond 3 TeV if you want to explain everything. So that comes to the conclusion that it's difficult to accommodate this is the case, but it's still possible within certain scenarios. And let me see, just the time, 50 minutes. So yeah, and finally, just to cover what also other directions that people have been thinking about. And here I should mention this possibility, which is based on the fact that you have missing energy. So you don't know if these are neutrinos, you don't know if they're left-handed neutrinos. So you could have a decay of a B into a K, and then some particle that will decay invisibly or that will fly out of your detector, right? And then so this particle that has to be light, so below the B mass, so below 5 GeV. And this is a viable possibility as well. And here the point that these guys made is that when you look at the Belle-II paper, so this is the plot that they have. So they have some partial information, preliminary information on this Q-square distribution that's still convolved, so convoluted with some experimental efficiency. So you cannot really extract the things that I was talking about before. But the thing you can look is to see where the excess appears. And here the point that they have made is that it is localized to some extent. Still within large uncertainties. But then if it's localized, this could be a good fit for these models, because this is a two-body decays, different from the three-body ones that I mentioned before. So the Q-squared distribution must be big. And then here they play the game and they show that you can still have a good fit if you have a particle that have a mass of 2 GeV, so that will be peaked here. And then when you smear this with this experimental, with the detector efficiency and so on, you get something that can still explain data. And that's also interesting because it goes in a different direction. And also because it motivates different searches where you can try to optimize the search for these two-body kinematics and to see if this is possible or not. Okay, so that's all. Now, for the summary and outlook, so the take-home message from this talk, I think that this is a very interesting case, especially because they're theoretically cleaner in comparison with the muon counterpart. But as of now, we have a reasonable understanding of the standard model uncertainties for these observables, but one still has to be cautious about what are the inputs that one uses for the form factors, and in particular the CK matrix L. And this will be very important with the future Belle-II sensitivity if you want to use these guys to problem physics. So, and here we expect some progress on the lattice QCD side, but also it will be very useful to have some experimental information that would be that would guide us to constrain, for example, these form factors. So that's why I think pin data is very important. I have also discussed how this ratio of low and high Q-square Branchy fractions can be used to constrain the shape of these extrapolated form factors. And concerning the ambiguity on the CKM matrix, that remains a problem, but we hope that other Belle-II concerning the charged currents will be useful also to understand what is going on there, together, of course, with new lattice calculations. So things that we can learn from this decays for example, this expression of C9 mu that's independent of the form factors. I think that would be very interesting when we'll have precise bin data. And finally, as I have shown, there is a small excess. I don't think there's a reason to be too excited as of now, but it's interesting to see that it can be fitted in a consistent, effective field theory approach. And for that, you need the couplings with the taus. Okay, so that's the main ingredient. And the important thing is that there are many cross-checks that can be done in the future to know if these experimental results actually does have a deviation from the standard model. So they can do different tagging. They can look at the case of the K-star, this angular distribution, so the FL, and also to measure the decays with neutral beam measurements, which is in principle different and experimentally, and that could be a useful piece of information. And the conclusion is that I think this is the first result of Belle-II that's really exciting. And then, I mean, just at the beginning, so there'll be a lot of more data and many opportunities to learn more about the standard model and physics beyond the standard model. So we all look forward to that. Okay, thank you very much for your attention.
Thank you very much, Olcyr, for the very nice and complete talk. Question from the audience? Olcyr, in the two model, Ogoras, please.
Somewhere on the page 19 or 20, you showed those bars, standard model and the Belle prediction. Now, this standard model is very narrow, and yet you say that the uncertainty of the CKM matrix element is an open problem. Here, the deviation seems to be so far away that it does not seem to be a problem, or do I understand something wrong?
No, absolutely. So this is the point I want to make. So today it's not a problem, but the point is that in the future, they expect to measure this with 10% precision. And then what you do with the CKM will become very important. But when you think about this, there is an ambiguity of what you take. It's just that as of now, it's too small to have an impact, but in the future, it can have. And I think here I even split uncertainty. So this is the part of the form factors, and this is the one of the CKM, which is two times larger than the one of the form factors. Yeah. But I fully agree, yes. As of now, it's not a problem. Yeah.
Okay.
Yeah, so you can see it's a 20% uncertainty, and they expect to measure this with 10%. So this can be a problem in the future.
Thank you.
You're welcome.
Bastian?
Can you go back, to this one again? The slide 20, please. The next one, yes. Maybe I didn't understand very well this square, this plot. Could you, because in gray you say, this is the first Belle-II results, but in the red are the new Belle, and what about the blue?
Yeah, so the blue ones are from the previous B factors. So Belle, that was the predecessor of Belle-II, and Babar, that was in Stanford.
Okay.
And you see, and then so here's they didn't see any excess from zero basically. So they were able only to place upper limits. So they didn't have a measurement like we have now for the first time. So this is 3 sigma away from zero, a bit more.
The inclusive one in the red case is
this is the only one where you actually see a signal above backgrounds, no?
Right.
Because it's the most precise. But then, of course, a very important cross-check would be to watch this hadronic and to see. So when you shrink the uncertainties with more data, this will go away for zero, and then you can see if the two different tagging methods give the same result.
Mm-hmm.
And also, you can see that from the previous B factories, the most precise measurement was the semi-leptonic one. But Belle-II has not done a semi-leptonic analysis yet. So that would be something between the hadronic and inclusive method in terms of precision that could also be a cross-check. So I have this law of triangle in order to find the same answer.
And maybe I didn't understand very well this, but
Which part?
I mean, in order to make your predictions, I understand that you used CKM data into as inputs in your into your calculation in order to predict something and then to compare to the data. But what are the experiments that are going on in such a way that you can reduce those uncertainties and you in such a way that your predictions can be more precise in order to conclude about new physics or whatever?
Yes, very good. So yeah, as I said, so this is not a problem now, but can be a problem in the future, no? And basically, I think the main players for in terms of the CKM matrix are Belle-II and LHCb. Okay, so you want to measure these guys as precisely as you can, and actually Belle-II even more than LHCb because it's a cleaner experimental environment, even though we have many less B measures. And basically, they are trying to measure this decays the most general way, so with a complete angular distribution. And then what you need is, again, an input from this form factor so you can extract the VCB that appears there. And from that, you can get VTB, VTS. Yeah, so this is the slide that I skipped. We're hoping there are some preliminary results, and also there are some new lattice results, and we were really hoping for many years. So this is a discrepancy that's more than 10 years old, even way more, I think. And we're hoping that new lattice results would be able allow us to really pin down this form factor so that when you compare with data, you can extract this VCB matrix element. But this is what I'm trying to show here. So for the first time, we had the lattice data for this B2D star decays that do not only fix the normalization of the form factors, but also the Q-squared shape. And as you can see here, there is some incompatibility between Belle-II and this lattice calculations between the red and the green and black points here. And this is a problem. So it's so we really need some progress here by combining theory experiment to really understand what is going on. And this is, by the way, the decay that has the most precise determination of VCP. That's the further away from the inclusive one. So it's a puzzle, and it's definitely very important to solve it if you want to keep pushing the precision frontier, because we're reaching a point where the parametric uncertainty is so damn important. I don't know if this answers the question.
Yeah. No, I'm not sure. I was thinking about this red curve from lattice QCD. It can be new physics behind that.
Yeah. Okay. So this is a different question.
Okay.
So you can think if it's true that so here that they're comparing the experimentally measured branching fraction with the inputs for this function that depends on the form factors, right? And then to extract VCD. But imagine that you have new physics. So then you'd have additional contributions here that could deform this Q-square shape, you know? So W and Q-square is the same thing. It's just a change of variables here that motivated by heavy quark effective theory. Okay, so that's a very good question. But the problem is so this is data with electrons and muons, and then when you try to put an operator that would try to fix the shape of these two, you need very large couplings that are very difficult to realize in concrete models. So I don't think this is the solution. It's more a problem between lattice or experiments. So someone has some systematic uncertainty that is having an impact on the shape.
Well, it's I guess that is pretty technical. It was just my guess. Immediate guess.
So lattice QCD is definitely the best way you have to fix this form factors, but that's also very complicated, and there are several ways several lattice QCD setups that you can use. So it's not the first time that you have some kind of disagreement, and that what we have learned from history is that the best thing is to have many different calculations so you can compare them with different approaches, and usually in this way you can get to a conclusion that will allow us to pin down a hadronite quantity. And so yeah, so some work will be needed here, if you definitely.
Okay. My last question is, in your I didn't connect very well your initial scheme, let's say, or assumptions that your effective field theory was based. I understood that it was based on the fact that the cutoff of your effective field theory was much higher than the electroweak BEV. For instance, in the first line. But to me, my interpretation of that is that all the new physics that is behind these these effective field operators, they must have masses above the electroweak BEV. But at the end of your presentation in the hidden sector part, you showed some conclusions regarding light mediators with 5 GeVs.
Yes, so, that's a different story. So yeah, I should have been more clear. So here we make this assumption that the physics is above the electric scale, no? And then when you build an EFT, when you do so, then you have to use the symmetries that you have at your disposal at this scale. But look, this was one possibility. Okay, and then the other possibility is the one that just, okay, what if we have a light mediator? So what changes? Then you're right. So the EFT that you formulate is different because this is not the gauge symmetry that you have. And then when you formulate your FT, you have to take into account these new particles because there will be light degrees of freedom that have not been integrated out. So it's a different kind of EFT that you formulate. So it's a completely opposite scenario. Yeah. And I think the main prediction then, the main difference in them is that you have a two-body decay. So it's something that's always peaked at Q square, which is not the case for the operators that I discussed before, where new physics is very heavy, you know?
Yes, I see.
Yeah, so this is the special feature.
Okay, thank you very much for your presentation.
No, thank you for the questions.
Boris?
Yeah, can one do similar measurements for D mesons?
D mesons, okay, so you mean like D to pi neutrino, no?
Also can go to the peak of psi prime and decay to D mesons.
Yeah, so yeah, we have Belle-III, which is an experiment in China that's dedicated to D mesons, but I'm not sure if they can do this measurement. Yeah, and okay, well, one important thing between a difference between the B and the D decays with neutrinos is that for the D decay, so if you go back to this gene mechanism, so I told you before that we had the top quark, no? So that's why you had this branching fraction, which is 10 to minus 6 and so on. Now, if you do the same for the D mesons, then you have the masses of the down type quarks here, and the largest one is the B quark, which is much smaller. So the branching fractions for D to pi nu is completely negligible. I mean, it's very, very small. But you still could think of that as a way to look for new physics. But experimentally, I think it's hard just because we don't have the right setup, like here we have for the B decays.
Okay, thank you.
Yeah, you're welcome. Thanks for the question.
More questions from the audience?
But you can do the same measurement with chaos. Just, but yeah, that's a different story. Yeah, K to pi nu.
Boris, do you have more questions? Or the other member of the audience? Olcyr, I had one question in the slide that in which you show a couple of examples, one with leptoquarks and the other with C prime. What about the scenario, for example, of having a scalar and maybe non-universal, that coupled non-universally with lepton and quarks? Maybe that scenario could also be used to accommodate the excess. Or do you think that these are more? What was the reason for you to choose this example? These are more motivated than an uncolored scalar with flavor violating interaction.
Yeah. So the problem in this case is that you need a coupling of a scalar, no, to the neutrinos, no, that are left and right-handed, no. Yes. Okay, so
I see. Yes, it will not be
Yeah,
possible
so-
to declare the handle.
yes, yeah, so because of so first it does not correspond to operators that I consider here, no, because it will be something of scalar type, and then for that you need a right-handed neutrino. So that's the reason, no? Because have a scalar that couples to a left and a right-handed, no, that's the way you can make it. So you have to assume that in addition to the scalars, you have a new so you have a right-handed neutrino zone.
It will be made the
Yeah,
family
it is possible. So it just goes beyond the assumption that I made here that neutrinos are purely left-handed.
I see.
So you have to add these two ingredients. Yeah.
Thank you, Olcyr. You also mentioned that these results may be sensitive. Yes, they are sensitive with this measurement of the CKM matrix element, for example, BCB. Do you think that, for example, because there can be extension of the standard model with heavy vector line thought partner, in which there can be deviation from unitary to the CKM quasi-symmetric, where this deviation could be small, but there are some bound and some room for having deviation from unitarity. I suppose that this will not affect so much the constraint regarding this coefficient, this Wilson coefficient, right? Or the sensitivity will be, all these are highly sensitive to deviation from the departure from unitarity of the CKM quasi-symmetries.
Yeah, definitely the CKM matrix can set limits on this kind of models, no? So this discussion about the shape of the form factor is completely independent of that, because you cannot change the shape of. But it's true that this could spoil this relation. So when I use the three-level process to fix BCB, and then I use that to predict B Kν, this does not work anymore when you have new contributions from vector-like quarks, no? And then what happens is that I have to be model specific. You have to determine VCB in your specific setup. I think this is the way I see it.
So it will be mostly model dependent. I mean, in that case, the effective field theory formulation, one has to go beyond the effective field theory formulation.
Yeah, so I think what happens in the end is that you have to add other operators that would allow for this kind of because you can always integrate out the heavy quarks, and then you end up with an effective operator that will be similar to this here, actually. And then that's the way. But yeah, it would go beyond what I'm doing. And in any case, I think these contributions are already constrained to be small, so they cannot have an impact here of the size that we're actually seeing experimentally.
I see.
But yeah, you need more pieces in this puzzle, no?
Yeah, maybe it's just the correlation between, for example, Cavivo anomaly and the flavor anomaly will be weak in that case, maybe, because this is constrained, this is a small unitarity deviation, possibly.
Yes.
Maybe weak the correlation.
Yeah, but it has to be small, not this effect, because especially because we're using a three-level process, and the contributions from new physics, so this three-level process has to be small also. So when you propagate this to the B Kν decays, I think it cannot be as large as we have here.
Thank you very much, Olcyr.
Thanks to you and to everyone for connecting.
More questions from the audience? If there are no more questions, we thank Olcyr for the very nice and very complete talk. Thank you so much, Olcyr.
Thank you, Antonio, for the invitation. Okay.
You're welcome.
Bye-bye.
See you in the seminar. Bye.
See you. Ciao, ciao.
Thank you.
Ciao.
Bye.
Ciao. Bye. Very nice.